Hello dear students, today is the first lecture for mathematical statistics subject. The first topic in mathematical statistics subject is mathematical expectation. In chapter 1 we discussed the sample mean, which is the arithmetic mean of the data. Now consider the following. If two coins are tossed 16 times and x is the number of heads that occur per toss, then the values of x are 0, 1 and 2. Suppose that the experiment yields no heads, 1 head and 2 heads, a total of 4, 7 and 5 times respectively. The average number of heads per toss of the two coins is then as follows. This is an average value of the data, and yet it is not possible outcome of 0, 1 and 2. Hence, an average is not necessarily a possible outcome for the experiment. For instance, the salesman's average monthly income is not likely to be equal to any of his monthly paychecks. Let us now restructure our computation for the average number of heads so as to have the following equivalent for the numbers 4 over 16 and 7 over 16 and 5 over 16 are the fractions of the total tosses, resulting in 0, 1 and 2 heads respectively. These fractions are also the relative frequencies for the different values of x in our experiment. In fact, then we can calculate the mean or average of a set of data by knowing the distinct values that occur and their relative frequencies without any knowledge of the total number of observations in our set of data. Therefore, if 4 over 16 or 1 over 4 of the tosses result in no heads, 7 over 16 of the tosses result in 1 head, and 5 over 16 of the tosses result in 2 heads, the mean number of heads per toss would be 1.06, no matter whether the total number of tosses were 16, 1,000 or even 10,000. This method of relative frequencies is used to calculate the average number of heads per toss of two coins that we might expect in the long run. We shall refer to this average value as the mean of the random variable x, or the mean of the probability distribution of x, and write it as mu x, or simply as mu, when it is clear to which random variable we refer. It is also common among statisticians to refer to this mean as a mathematical expectation or the expected value of the random variable x, and we denote it as E of x. Assuming that one fair coin was tossed twice, we find that the sample space for our experiment is h and h, h and t, th, tt. Since the 4 sample points are all equally likely, it follows that bx equals 0 equal b t of t 1 over 4, bx equal 1, b t of h plus b h t equal half, and bx equal 2, b h equal 1 over 4, where a typical element, say th, indicates that the first toss resulted in a tail followed by a head on the second toss. Now these probabilities are just the relative frequencies for the given events in the long run. Therefore, mu, or the expected value of x, equal 0 times 1 over 4 plus 1 times 1 over 2 plus 2 times 1 over 4 equal 1. This result means that a person who tosses 2 coins over and over again will, on the average, get 1 head per toss. The method described above for calculating the expected number of heads per toss of 2 coins suggests that the mean or expected value of any discrete random variable may be obtained by multiplying each of the values x1, x2 until xn of the random variable x by its corresponding probability f of x1, f of x2 until f of xn, and summing the products. This is true, however, only if the random variable is discrete. In the case of continuous random variables, the definition of an expected value is essentially the same with assumptions replaced by integrations. Let x be a random variable with probability distribution f of x. The mean or the expected value of x is mu equal e of x summation x for x times f of x if the x is discrete, and mu equal e of x for integration from minus infinity to plus infinity for x times f of x dx if x is continuous. The reader should note that the way to calculate the expected value or mean shown here is different from the way to calculate the sample mean described in chapter 1, where the sample mean is obtained by using data. In mathematical expectations, the expected value is calculated by using the probability distribution. However, the mean is usually understood as the center value of the underlying distribution if we use the expected value, as in definition 4.1. For example, a lot containing 7 components is sampled by a quality inspector. The lot contains 4 good components and 3 defective components. A sample of 3 is taken by the inspector. Find the expected value of the number of good components in this sample. The solution is: let x represent the number of good components in the sample. The probability distribution of x is f of x for combination x times 3 combination 3 minus x divided by 7 combination 3, and the x takes values 0, 1, 2, and 3. Simple calculations yield f for 0 equal 1 over 35, f for 1 equal 12 over 35, f for 2 equal 18 over 35, and function of 3 equal 4 over 35. Therefore, mu equal 0 times 1 over 35 plus 1 times 12 over 35 plus 2 times 18 over 35 plus 3 times 4 over 35 equal 12 over 7 equal 1.7. Thus, if a sample of size 3 is selected at random over and over again from a lot of 4 good components and 3 defective components, it will contain on average 1.7 good components. The second example is a salesperson for a medical device company has 2 appointments on a given day. At the first appointment, he believes that he has a 70% chance to make the deal. from which he can earn $1,000 commission if successful. On the other hand, he thinks he only has 40% chance to make the deal at the second appointment, from which, if successful, he can make $1,500. What is his expected commission based on his own probability belief? Assume that appointment results are independent of each other. Solution. First, we know that the salesperson for the two appointments can have four possible commission totals: $0, $1,000, $1,500, and $2,500. We then need to calculate their associated probabilities by independence. We obtain the function for 0 equal the follows: 0.28. The function for 1,000 equal 0.112. Therefore, the expected commission for the salesperson is the expected value of X equal $1,300. Example 4.1 and example 4.2 are designed to allow the reader to gain some insight into what we mean by the expected value of a random variable. In both cases, the random variables are discrete. We follow with an example involving continuous random variable, where an engineer is interested in the mean life of a certain type of electronic device. This is an illustration of time to failure problem that occurs often in practice. The expected value of the life of a device is an important parameter for its evaluation. Let X be the random variable that denotes the life in hours of a certain electronic device. The probability density function is as follows. Find the expected life of this type of device. Using definition 4.1, we have the following formula for the expected value of X. Therefore, we can expect this type of device to last on average 200 hours. Now let us consider a new random variable g of x, which depends on x. That is, each value of g of x is determined by the value of x. For instance, g of x might be x squared or 3x minus 1, and whenever x assumes the value 2, g of x assumes the value g of 2. In particular, if x is a discrete random variable with probability distribution f of x for x equal minus 1, 0, 1, and 2, and g of x equal x squared, then probability of g of x equal 0 equal function of 0, probability g of x equal 1 equal probability x equal minus 1 plus probability x equal 1 equal f of minus 1 plus f of 1. Probability g of x equal 4 equal probability x equal 2 equal function of 2, and so the probability distribution of g of x may be written as follows. By the definition of the expected value of random variable, we obtain mu g of x equal expected value for g of x, which is equal summation of g of x times f of x. This result is generalized in theorem 4.1 for both discrete and continuous random variables. Let x be a random variable with probability distribution f of x. The expected value of the random variable g of x is mu g of x equal expected value of g of x equal summation g of x times f of x if the x is discrete random variable, and mu g of x equal expected value of g of x for the integration from minus infinity to plus infinity for g of x times f of x dx if the random variable x is continuous. Thank you.